Okay, so we saw the definitions of symmetric and skew symmetric matrices, and then a few special cases for any square matrix A, which you can write as n by n. If you take A transpose times A, or A times A transpose, or A plus A transpose, these are all symmetric. And if you take A minus A transpose, it works out to be antisymmetric. Okay, a few other definitions. Something what is called as an idempotent matrix. If a square matrix satisfies A square equals A, or basically A times A equals A, it is called idempotent. Or a more general case, a periodic matrix. If you can show that A to the power of k plus 1 equals A, then it is periodic of order k. And the special case is if k equals 1, you have A square equals A, which is an idempotent matrix. A few other definitions. Nilpotent matrix. If there exists a power k such that A to the k is 0, where 0 is the null matrix, and A to the k plus 1 is not 0, then A is nilpotent of order k. So the order is k. An involutory matrix. If A square equals I, where I is the identity matrix. Just to recap, identity means all the diagonal elements of the matrix are 1 and all the non-diagonal elements are 0. And the last definition, orthogonal matrix. So any square matrix A is orthogonal if A times A transpose equals I. So if it satisfies this condition, the matrix A is called to be orthogonal. Okay, so now that we have seen the special types of matrices, we can move on to what is known as the adjoint and inverse of a matrix. Again, these operations on matrices only work for square matrices. So if A equals Aij n by n, then the definition of the adjoint of this matrix, and it is written in abbreviated form as adjoint of A, is defined as the transpose of the cofactors of this matrix. So from one of the previous sections where we defined what the cofactors of this matrix are, and you take the transpose of that, that gives the adjoint, where Cij is the cofactor of element Aij in A. Let's take a quick example. Let's say you have a matrix such as x, 3 0 2 1 6 0 0 9 7. So calculate the adjoint of this matrix. Well, to find the adjoint, you first need to calculate the cofactors of this matrix. So let's start off with the cofactor of element A11. So C11 is minus 1 to the power I plus j. So 1 plus 1 times this minor. So it's 6 0 9 7 equals 42. And so you can keep doing that for all the elements, and then you can find out that the adjoint of this matrix is the transpose of the cofactors. And this is an exercise for the listener. You can calculate each of these terms and verify that this works out to be 42, 18, minus 12, minus 7, 21, 2, and 9, minus 27, 18. So that is how you calculate the adjoint of a matrix. So before we move on to inverse, we need to look at some properties of the adjoint. So for some special cases, like adjoint of the null matrix is again the null matrix, adjoint of the identity is again the identity matrix, adjoint of a scalar is a scalar, adjoint of a diagonal matrix is also a diagonal matrix, then this is important. So if you take the adjoint of the transpose of a matrix, it is the same thing as taking the transpose of the adjoint of the matrix. So these two operations are interchangeable. And then if you take the adjoint of a scalar multiple of a matrix, it is lambda to the n minus 1 adjoint of A, where n is the order of the matrix. Then for product, if you have two matrices multiplied A, B, and you take the adjoint, then the order flips. So it becomes adjoint of B times adjoint of A. And then if you pre-multiply an adjoint by the matrix itself, doesn't matter the order in which you do it actually, times A. The result is simply the determinant of A times the identity matrix of nth order, where n is again the order of the original matrix. And then if you take the determinant of the adjoint of the matrix, that is the determinant of the matrix to the power n minus 1. If you take the adjoint of the adjoint of the matrix, the value comes out to be the determinant of matrix A to the power n minus 2 times A times the identity of order n, and then if you take the determinant of the adjoint of A, that simply comes out to be the determinant of A to the power n minus 2. And one last thing to note, a square matrix A is said to be singular if determinant of A equals 0. Clearly, if the determinant of A is non-zero, A is said to be non-singular. So with these properties and having studied